Hello, everyone, and welcome back to CSE 373. Today, we are continuing our journey into the discussion of sorting and kind of our sorting day 2. And as a reminder, this is kind of the last day of real content for the course, the core content that we care that you know about, and we will assess you on in exercise 5 and exam 2. The idea of sorting is very, very important when it comes to the world of algorithms. In this video, I'm going to start off by recapping what we learned on Monday so we can contextualize what we're learning today. In the highest sense, today we're learning 2 new algorithms to go on top of the pile of sorting algorithms we already know. But these ones will have a very slightly different flavor to them of how they work, and we'll find that they're actually going to be very efficient. And they're the ones that you probably see out there in practice. Like whenever you call Java a sorting function, these are the ones that it's probably using in most cases. So we'll get there in the next videos. But in this video, I want to start with highlighting kind of what we learned on Monday. So on Monday, we introduced the problem of sorting. And sorting was this nice kind of easy problem to describe. You just sort a list of values. But it was so abstract that we had to give a lot of terminology and definitions to make it work in all possible cases. So we introduced the notion of a sorting relation or an ordering relation, which is how elements should be ordered. You know, when we think about ordering a list of numbers, we sometimes take for granted how there's a natural ordering of 1 comes before 2, comes before 3. But sorting algorithms don't necessarily care if it's just numbers. We want to make these more generic to work for anything. And so we use this idea of an ordering relation to tell us how elements should be ordered. So for example, you could change your ordering relation for the integers to be decreasing order. So use the greater than for your ordering relation. And this idea of adding this abstract notion of ordering relations lets it work in more contexts. So you can work with more complicated pieces of data like movies that might have names or years, and you could define whatever ordering relation you want to sort by for your application. And you can get even more abstract with data like image data, where it's not always so clear how you should order them. You could do something fancy like try to analyze the colors of the images and try to sort based off this, like red images to blue images or something. Whatever your application needs, if you can define an ordering relation, you can sort it. And the algorithms we introduced work in this kind of abstract sense of just ordering the values that are present based off whatever ordering relation we saw. So when we talked about sorting, it was sorting a list of values based off their ordering relation. We talked about a couple other properties that we see from some sorting algorithms. The first is stability. And stability is all about when there are duplicates, how you break ties. So there are lots of sorting algorithms, and some of them are stable. If it's stable, it means if there are ever ties, it leaves them in the order in the original list. So for example, I have this list of artist, name, and year, and I have 2 valid sorts. They're both correct. They sort them based off the ordering relation, which I defined as using just the name. Both of those sorts are valid, but the first is stable while the second's not. And the first one's stable because all of the cases that are ties, Anita and Duska, those entries are ordered based off their order in the input list. So it keeps their ordering from the original list if there's a tie. That's all that stability means. And there are some contexts where stability might be necessary based off your application, and others you might not care. Whatever your use case is exactly how you determine which one of these you should use. So we'll talk about this a little bit later today, which is we're going to give you these kind of 5 sorting algorithms that give you a broad set of tools to use in whichever situation you see fit. Now, the other property of these sorting algorithms that I didn't formally define, but we did use on Monday, was this idea of an in-place algorithm. This is a common term that we use, not just for sorting, but in a lot of algorithm design. In place just means without using extra memory or using like an excessive amount of extra memory. So when we talk about a in-place sorting algorithm, what I mean is one that doesn't have to create an extra array to store all the values. So we've talked about selection sort, insertion sort, and in-place heap sort that can all be done in the input array. And if something needs extra storage, like needs another array, then we'd call that something that's a not in place sorting algorithm. So those were kind of our abstract definitions. And then we talked about a couple algorithms that use this strategy of iterative improvement, where we kind of have a section that we have sorted and we slowly grow that section over each iteration of our algorithm. So something like after k iterations of our loop, the first k elements will be sorted. And we talked about two frustratingly similar algorithms, but have very different details that use this idea of iterative improvement. We talked about selection sort and insertion sort. And both of them have the same setup, where you have a sorted section at the front, kind of the current item you're considering, and then an unsorted section at the end. Now, they both use this setup, but they differ in what they do and why. So selection sort is always starting with the current item and scanning towards the end through all of the unsorted items. And if you go through there and find the smallest item you can, and then swap it with the current item. And if you do that, that will grow your sorted region by 1, because in the earlier iterations, you grabbed the smaller items. And so every iteration, you're growing this kind of sorted region by 1. Now, we said that this would run into a worst case runtime of n squared, because you have this kind of nested for loop over the length of the array behavior. And this algorithm doesn't really care about what values it has inside of it. It's always going to run to the end each time. And so its best case and in practice case are going to be exactly the same as the worst case. We also said that this was not a stable sort, because one detail is whenever you find that smallest value, once you've determined it, you swap it with the current item, which then maybe moves the current item to a totally different spot than it originally started. And so you can't guarantee stability from these. We then also introduced this other algorithm, insertion sort. And the job of insertion sort was to have a similar setup as before, but the key difference is that how it decides what to move and where it's moving to differs than selection sort. So the idea is that in insertion sort, we take the current item, and instead of scanning for all of the unsorted region, we don't care about the unsorted list in insertion sort. All we care about is taking the current item and inserting it in its proper place in the sorted items. So in insertion sort, we instead scan through the sorted items, find the proper place, and then shift everything over and place it in the right spot. Different perspective, kind of same setup as before, but yields a very, very different algorithm. So in the worst case, it's still going to be n squared runtime. The reason being you have to shift kind of n things over n times, and you can get this quadratic behavior. But in the best case, maybe if the list is already sorted, or mostly sorted, you don't really have to do a lot of shifting. And so this insertion step might be more efficient, meaning that you can get something closer to O of n, and in the truly best case, exactly O of n. And in practice, we'll see something more like O of n squared. Now, one nice thing about insertion sort is it is going to be a stable sort, because we aren't swapping things from different parts of the array. And just like with selection sort, it will also be in place. You will almost always use insertion sort over selection sort. It's generally just a better sort because it has that better best case, and it's stable without being slower. So that's a general reason why to use insertion sort over selection sort. Now, the other sorting algorithm we talked about, the third one, was heap sort. So it uses this very intuitive idea of whenever we need to find the minimum in selection sort, what if we put that in a heap, because heaps are optimized for finding the min? So the idea was put it in the heap and just keep removing min over and over and over again. Now, that worked well in theory, and we got that n log n runtime, but we saw a downside was it wasn't in place, that we had to use this heap to build up. And so we talked about the idea of in-place heap sort, one that builds the heap inside the array itself, and we always work inside just this input array. So we use the array representation of our heap, and then went through and kind of, after heapifying it, always remove the min, which decreases the size of the heap by 1, opening up a free space at the end. And we take that minimum value and stick it at the end. So we'd say, oh, okay, we're going to put 1 at the end. And because this is a heap, we always take the element that used to be last, move it to the top, and let it percolate down. And so we do something like just put the 22 at the top, and then let it percolate down to its right spot. And then we have kind of our new heap. But the idea is after I remove min, this heap size decreased by 1. This opened up a free slot at the end for us to store the value we just removed. And we just do this over and over again, which will end up building up the list in reverse order. But we can easily fix that either by just reversing the list, which is actually an O of n operation, or you could change your heap implementation to be like a max heap or something like that instead. So that was kind of everything we talked about on Monday. We talked about the iterative improvement strategy, the imposing structure strategy of using heaps. And now I want to talk about a kind of completely different strategy that's going to underlie both these new sorting algorithms we're going to talk about, merge sort and quick sort. So in the rest of this video, we're going to highlight what this new strategy is and describe the merge sort algorithm. And the next video, we'll talk about what this quick sort algorithm is. So this new strategy I'm going to introduce is what we call divide and conquer. So here's how the general strategy works. This doesn't describe a specific algorithm, just a very general problem-solving strategy when it comes to designing algorithms. The first step is you divide, and then the next step is you conquer. So this kind of matches our experience with names from computer science that are both not informative and also not cool. That's all it is. It just says divide and conquer. Now, there's also an extra step, which we usually talk about being combining the results, but for some reason, combining wasn't cool enough to make in the name divide and conquer. So what we do in this divide and conquer strategy is you take your problem and break it up into smaller instances of your problem. So you break it up into smaller pieces, conquer those pieces by solving them, and then combine the results into kind of your overall picture. This is a very, very broad way of kind of describing a problem-solving strategy. And in many contexts, you might see slight variations of this where the conquering step doesn't require maybe any extra work on its own. It's just recursively kind of solving the problem. And that's actually what we're going to see here is that of the algorithms we learned today, divide and conquer looks like a recursive solution to a problem, where you break your big problem into smaller versions of itself and solve it recursively, and then somehow combine the results from those recursive calls. So as kind of a like pseudo code, this like very meta code describing what divide and conquer does, we'll have some kind of setup where we kind of have a base case. If the input is small enough to solve, like size 1 or size 0, I know how to solve it. Then we just conquer that one step and we can return it. Otherwise, if we're kind of in this case with a lot of input, we need to divide up that input into smaller pieces, recurse on those smaller pieces, and then combine those results. So divide, recurse so we can eventually conquer all of the pieces, and then come back and combine them. So this was all wonderfully abstract and probably didn't make a ton of sense. It makes a lot more sense with a specific algorithm. The first algorithm we're going to talk about is this one called merge sort. This slide is going to have a lot of information. We're going to come back and visit each part in detail. Here is the big idea of merge sort following this divide and conquer strategy. We start with this really big unsorted array in pink. We then divide it up into 2 subarrays, just divide it in half, first half of the elements, second half of the elements. Then we recursively merge sort those. That will go off and it will eventually hit some base case where we have some kind of elements of size 1 or lists of size 1, which are sorted by definition. Any list of length 0 or length 1 has to be sorted because there's no way it's unsorted. Then once we get to these kind of base cases, we can come back and start combining them. And merge sort combines these sorted arrays in a very clever way. It calls merging them, which is why it's called merge sort, and such that we can get a sorted array for our overall original problem. So super high level description, it will make a little bit more sense when we go through and talk about each part more explicitly. So first, we start with dividing. So we divide our array in half, and this division step and this divide and conquer algorithm is going to be applied recursively. So we keep splitting this array in half over and over again until we get to a list of length 1 or 0. Now, you might be wondering already what happens if there's an odd length array. Generally, you just uh, uh, I was going to try to say a phrase here. Generally, just leave one extra on one of the sides. It'll just be slightly imbalanced, but only by a difference of one. So we just keep splitting it up, split up, split up, split up, until we get down to our base case when there's no work to do. And this is kind of why I was in that last slide. There's no extra work for conquering, because once you divide it down to an array of length 1, you kind of solve that subproblem. An array of length 1 is already sorted. And so then it gets to our kind of combining step, where we actually need to combine these kind of subarrays into a sorted full array. Now, it might not be clear yet exactly why we're breaking it up or how we put them back together. That's what we talk about the merge step. But the idea is, by breaking this larger problem into smaller ones, we're hopefully making our lives easier, because we don't have to worry about kind of handling all of these cross data dependencies from the left side and the right side of a split, until hopefully later when it might be easier to manage. So first step, divide everything in half over and over and over again. Then once we've done that, once we have these length 1 arrays that are already sorted on their own, we now need to get to this combine step of combining our results together. So we are going to do this with recursion. So we divide up recursively, and we have our subarrays that came back to us sorted. We're just going to assume that merge sort is magically working. It returned us those 2 subarrays that are sorted, and now I need some way of merging them together. And this is kind of like the bread and butter of merge sort, is the merging operation. The idea is you went off and recursed, you divided your array in half, you recursed, and merge sort magically went off and sorted those subarrays. So now you have 2 sorted subarrays back. Remember, if you took 143 as Stewart, he would shout, "Believe in the power of recursion," right? We are going to assume it works. We get our 2 subarrays back, and then we need to merge them together. And so the merging algorithm is a very clever algorithm. The notion is, well, it's easier to sort 2 subarrays that are already sorted than trying to just sort them on their own if they're unsorted. The idea is, keep track of 2 fingers. At the start of each array, keep track of a pointer. Then, when you want to merge them, you kind of just run your fingers across the arrays, always grabbing the smallest value. So you look at 2 and 1, and you say, oh, well, 1's smaller, so take that. Now, since we already used the 1, move the finger in the right array over by 1 to 6. And now compare 2 and 6. Well, 2 is smaller, so take the 2 and move the finger for the left array over. You just keep repeating this process. Oh, the 6 is smaller, move the right finger over. The 7's smaller, move the right finger over. The 8 is, move the right finger over. The 8 is smaller, move the right finger over. So you always just grab the smallest and then update your pointer. And you just keep doing this forever and ever until you run out of values in your arrays. This totally works if your arrays are slightly different sizes. Once you kind of run out of stuff in the second array, then I'll just grab the rest of the stuff from the first array. So you just always grab, for each iteration of this merging algorithm, just grab the smallest and then update your state. Now this works because we only move the smaller pointer. We're going to be reconsidering, in some sense, the pointer we didn't move. We're going to compare that with the new value from when we just moved our pointer. And we're never going to get something wrong because these subarrays have been sorted. There's no way that we are going to make a mistake and have to go back and shift things over. So this works because we have these sorted subarrays to start with. Now, once you kind of run off the end, you're kind of done. So let me walk through one kind of full example of how this works. Here on the left, I've kind of have some pseudocode describing this merge sort algorithm. You start with your base case where it's a list of length 1, or I guess you can also say 0. And you just return the list in that case. It's already sorted. Otherwise, we need to do this kind of 2 recursive steps. So first, make a new array that contains the first half of the elements. So 0 up to the midpoint. So you have to compute kind of what's the first half index and make a new array with just those numbers. And then recursively merge sort that. Same thing with the right subtree or subhalf. Grab the second half of the array and go off and merge sort that one. And if we believe in the power of recursion, those will come back to us and we'll have 2 sorted subarrays. And then we just run this merging algorithm, running our fingers across, grabbing the smaller value each time, to build up our whole array. I'm not showing the pseudocode for that because it's a little detail oriented, but the idea is exactly what I just described in the last slide. So let me run through a full example of this. We start with this array. We're not in our base case, so we break it up in half, and we recurse on the left. So in this recursive call, we kind of we go into our recursive case because we aren't at our base case yet, and we break this array up in half. Well, then we hit our base case for both of these arrays. We just return that each individual arrays are sorted because they're each length 1. And then we have to merge these two arrays. Well, we start by grabbing the 1 and then the 55. Those will make the kind of returned subarray from this left call 155. Well, then we need to go back to where we were before and now recursively sort the right subarray. We'll have to now do this merge sort on the right side from our original array. Then it splits off, we hit the base cases, come back, and now we're kind of back in the original method call. We just got back our smaller half of the array, the larger half of the array, and now we need to merge them together. And so then we just run this algorithm, this merge algorithm again. We grab 1 and then 6, 7, and then 55. Oh my goodness, very complex just to sort. The question is, well, what's the runtime of an algorithm like this? Well, it turns out that the way we analyze this is exactly what we needed to do before with recursive things, where we had to come up with a recurrence. And so if we think about this, we'd find that the recurrence for this function would be something like 1 in our base case. Otherwise, it'd be 2 times t of n over 2, because we run this same algorithm on something half the size, and plus this n work for the merging. And also there's also this work for actually splitting up the arrays, right? When you have to make an array of half the size, that's still also going to be an O of n step. So we have this kind of like plus linear work. And if we plug this into Master's theorem or use the tree method, we'd find that this is n log n. Now, this also, one way we could figure this out is remembering our kind of constant size input patterns, where we saw that a lot of recursive functions follow some similar patterns, and merge sort was actually our example of this constant size input one, where it had a width of n at every level and a height of log n, or 2 log n, because we kind of go down log n and then down one more time. Now, it turns out that the best case is also going to be the same, as well as the in practice. No matter what the data actually looks like, merge sort always runs in the same time, because it kind of doesn't do anything based off the actual values in the array. It just keeps splitting in half over and over and over again. The nice thing about merge sort is that it's a stable sort, is that because we always kind of divide values that are close together and like into the same subarrays, that in the original list, that we don't change the order of the original list too much when it comes to breaking ties. You do have to be a bit careful when it comes to actually implementing this merge algorithm with breaking ties carefully, but I promise you that you can break ties in such a way that doesn't violate this stable property. Unfortunately for merge sort, even though it is this kind of fast n log n algorithm, it is a stable sort. It's not an in-place algorithm. The reason is we have to create all these extra arrays all the way down, and when we're kind of merging them together. So this algorithm will not be in place. Now, it can be slightly better. There's actually a very clever implementation of merge sort that actually only uses 2 arrays. You kind of flip back and forth between which one you're writing to and reading from. But that one's more complex than what we just talked about. It's still an n log n runtime. And before you go off and try to search for in-place merge sort, I promise you it actually does exist. Fortunately, it's much more inefficient. So we don't get this nice n log n runtime if you actually want it to be in place. And so in place is generally something people are okay sacrificing for this nice, simple runtime that's actually really, really efficient. In the next video, I'm going to tell you kind of a slightly different story about how to do this divide and conquer, where you're going to find the quick sort algorithm that takes some slightly different design decisions in terms of how it's implemented, and this affects kind of these overall results. But that's getting a little too far ahead of myself. We're going to talk about that in our next video.